Okay, next, let's move to the process and instrumentation diagram of P&ID. Okay, basically for P&ID, it can be defined as process. Okay, we have process here or piping and instrumentation diagram. So what is the difference between P for process or P for piping? So I will explain it later, but in general, P&ID is provide an additional level of detail for the overall design process. It essential for simulation and later construction and operation of the process. Usually, basically we focus on the instrumentation for P&ID. So it will help on the simulation and also later construction on the process. So this P&ID contains schematic for all piping, associated features such as valve, what type of valve used, whether globe valve, whether we have manual valve, so whether we have a gate valve. So basically it represents by each symbol, and we have a various component of instrumentation, including the type of line, whether this is pneumatic, hydraulic, whether this is electrical line. So it represent all information covered in P&ID, and also the control mechanism as well. What type of the control mechanism, whether open close or open to open. So it already mentioned in the P&ID. And this P&ID allow the design engineer to simulate a various operating condition and investigate the effect that these changes will have on the operability and economy of the process. So basically the P&ID are required as a reference while operating a process. So all the operator technician will refer to this master blueprint or P&ID to conduct a troubleshooting, to familiar or understand with the whole process. Okay, this example on the process and instrumentation diagram for the commercial integrated solar water heating system. So you can see here from this P&ID, basically we can understand that the location of the equipment. So example here, we have a water storage tank which consists of the heating system here. So we have a flush point. Okay, we have a flush point for each, maybe I can say for each main piping, and then we have a gas burner here. So basically we have two pump here, standby mode and operating and standby, and also run pumps. So we have a manual valve. We have two gas burner, maybe to support the water system, hot water storage system. And we have, this is the non-return valve to avoid any return back to the piping. And then we have the expansion tank at the upper of the hot water storage tank, and also we have thermometric vacuum tube collector here. So basically it almost mimic the real process. So we can imagine the real process of this commercial integrated solar water system. So this is this is not a standard P&ID, but I will show you how what P&ID is referring to the piping. So from this piping, basically P&ID or refer to the piping is the extent further information from PFD. Okay, for the piping, we mentioned about the size of the piping and also the material of the piping. So we start, okay, let's refer back to from the previous video, from the previous topic. So from this diagram, we know that we have one input and three output so far, right? So the input is here. So we start with here. So this piping has 3-inch schedule 40 and carbon steel, the material. So insert into tower T101 to purify it. So this is for benzene distillation. So we have benzene distillation. So at the top of the tower, so it installed with 12-inch schedule 10 carbon steel. So you can see here this the size of piping here is much higher compared to inlet, but okay, you can see here we have schedule 10 and schedule 40. Okay, if we has a higher schedule, that means it can stand to the higher pressure. So it should be this is has much higher pressure compared to at the top or the condenser area. And then it moved to the condenser. So we have a okay, this is the inlet for the cooling, which we use a 4-inch schedule 40, and we install the flow indicator, FI is flow indicator, which is the instrumentation that mounted on the equipment of piping. So flow indicator is mounted here. So you can see here, I can delete it first. So you can see here, this is the symbol of FI. So this is basically refer to the vortex types. We have a lot of type of the flow indicator. So this is for the vortex type. So we have this another flow indicator, such as we have the orifice meter. So it depends on the type of the flow indicator that we use. So it already defined or mentioned in this P&ID. And then we also have this. Okay, this is a temperature indicator mounted to control the temperature outlet from this shell and tube heat exchanger. So you can see here the main stream here from the tower insert into the tube side. So for the shell part, consists of the cooling medium. So we have a cooling medium on the shell side. So we have this pressure relief valve here to control the pressure inside this heat exchanger or condenser. And then this is from this after inserting into tube heat exchanger, it will move into the vessel V104. So the piping is 4 inches, schedule 40, and the material steel, carbon steel. And okay, for this vessel, it mounted with LE is lever element. So we have a lever element here. Basically, the lever element is not a physical instrument. It's just a signal. So mounted, connected with the lever transmitter. Okay, transmitter is the physical equipment or physical transmitter. Transmitter is the instrumentation or mounted on the vessel. And then to control the level alarm high or level alarm low, which is it will transmit the signal to level indicator controller before it transfer the signal to the level 2 computer. L1 is the computer output, and then it will send the signal to the level control valve. That's mean, example, how the mechanism is work. Okay, example, we set the level maybe 20 mm Hg. Okay, this is the setting or the desired level. And then after that, when the level is reduced, maybe 5, reduced to 10 mmHg, so the level indicator controller will receive signal from level transmitter that mentioned, okay, the level of in the vessel is too low. So it will trigger the level alarm low. So what happened to the level control valve? So level computer will receive the signal and pass to the level control valve, mention that, okay, you should increase the, you should reduce the range from 0 to 100%, right? Usual range. So it will reduce the range to ensure that the minimum flow of the component of the liquid here, output or outlet into this valve. So basically, when it reduced, maybe it reduced to 0.5%. So it will increase the level in vessel. So basically, this is how control system work. Okay, so we can control the outlet of benzene. Okay, so how about this? Okay, because we have also the recycle back into the tower. So this is the type of the piping, including the size and also the material. So we have, since we use two pumps, standby pump A and B, so we have two piping here. So basically, it will give the indicator for a flow indicator. So for flow indicator, there is no computer signal. So only we have a mounted flow transmitter or that give or indicate the flow rate of in the for this piping. So if we return back to the tower, so basically the flow rate of the benzene to return back to the tower will be controlled because we have a control system here. So you can see here, okay, this is, we have this, maybe this is the type of the flow transmitter. So example, we use the orifice meter. So we mounted with flow element, the flow transmitter, which is we have the flow element here. The flow transmitter will transmit the signal to the flow rate controller, and then it based on the flow alarm low or flow alarm high, and it pass the signal to the computer before we can ranging the control valve here, flow control valve, of the opening of flow control valve depending on the signal received here. So how about at the bottom? So you can see here at the tower, we have temperature indicator at the top, in the middle, and also at the bottom, we have a control system. So same, we have temperature element, which is temperature transmitter mounted on the vessel, and then it control the temperature alarm high and temperature alarm low before we connected to the temperature resistant controller, and it detect to the temperature computer to reach the temperature control valve. So this is how it works. So basically, and then we have this also use a shell and tube type. So we have a pressure relief valve here, and also for each process measurement here on this part, we have a record for the pressure, temperature, and flow. So we have all the measurement except the level here. So how about this part? So you can see here, so we have at the bottom temperature indicator and also pressure indicator. So we control the level of at the bottom because this level is connected to the reboiler. So example, if we have a lower, because we need to ensure that the reboiler is not run empty. So we can install we can introduce the lever element here. So we have lever element connected, which is mounted with the lever transmitter to control either alarm high or alarm low, and also the transmit the signal to lever indicator controller before connected to the lever control valve. So for the final product, we monitor its flow rate using flow indicator. So you can see here the instrumentation and then the mechanism of the process is detailed. So normally it will also help the instrumentation engineer to design the control system based on this diagram as well. So these are the detailed information based on the ISA. ISA is the Instrumentation Standard Association. So all the symbols should refer to the ISA. So if you can see here based on the symbol, okay, back to this, we have the circle, and then we have the first line here and also dotted line. How can we classify it? Okay, if we have circle without line, so that means the instrument located in the plant. There is no signal pass through to the system. So example here, so you can see temperature indicator, pressure indicator is located on the plant. So if we have single line, that means instrument located on the front of panel in control room. Okay, in industry, we have a control room that to control or monitor of the process, because there are risks if we install everything manually. So we need to control it, especially if related to the toxic process or maybe high temperature, high pressure process. So we may control it in the control room. So if the dotted here, dotted line, so basically located on back of panel in control room. So basically this is whether front on the panel, whether back on the panel. So back on the panel, that's mean we have a control on the panel itself. So these are the identification letter. So first, analysis, burner. So you may refer to this, but usually we common measurement is pressure. We have the temperature, level, L, and also the flow rate. So we have the second, so example Fi, we have flow indicator. So Fe, flow element. So these are the detail, or you may refer to this P&ID to more understand about this. And then, okay, this is the line that I mentioned. We have a capillary, that means the normal piping. Pneumatic use the air. Usually it refer to the control valve, whether we have pneumatic or hydraulic. And also we have the electrical. This is related to the signal, such as this is electrical signal to transmit the signal from the level indicator controller to the level computer output. Okay, this is exercise. I hope that you can try by your own, try to understand the diagram, and let's answer this together. Okay, what are the, okay, maybe you can try to answer this. Okay, I put the number of the question. So later you may try to answer this question. So D, what is the temperature output? Computer, right, related to the computer flow transmitter. So we have number 6. What is the number 1? Number 1 is the, okay, this is the link line. So we have the link line. So you can see that, okay, this is for the, because we have 2 process measurements. So this is the cascade, right? Cascade control. So we have the temperature and also pressure is linked together to perform this cascade controller. And we have the, this is the electrical signal, and this is the pneumatic line.